Hello my dear students, today we are going to discuss about carbon family. The group 14 elements are carbon, silicon, germanium, tin, lead and fluorovium. The group 14 elements form the second family among the p block elements. These include non-metal, metalloid and metals. The discovery of carbon family members are in the respective years, and some of the carbon family members are discovered in prehistoric times. Carbon exists in elemental state and in combined state. Silicon is the second most abundant element on the Earth's crust. Germanium is relatively rare in nature. Tin and lead are also not very abundant. These are the various forms of elements in nature. Here we discuss some aspects of group 14 elements. These include electronic configuration, atomic radii, density, melting point, boiling point, ionization energy, metallic character, oxidation state, catenation, allotropy, standard electrode potential and chemical properties. Firstly, electronic configuration. The general valence shell electronic configuration of group 14 elements is ns2np4. The next general property is atomic size. On moving down the group, atomic size increases. We know the radius of an atom is governed by two factors: the number of shells of electrons around the nucleus and the attraction of outer electron field from the nucleus. The attraction of the outer electron field from the nucleus depends upon the shielding effect. Shielding effect is the shielding of outer electrons by inner electrons, prevents outer electrons from feeling effective nuclear charge. That is, electron between the nucleus and valence electron repel each other and making the atom larger. Why atomic size increases on moving down the group? Do you know? We know as we move down the group, nuclear charge increases, number of shells increases in each step, causing the valence electrons to be farther from the nucleus, and shielding effect of the inner electrons increases down the group. The combined effect of increase in number of shells and shielding effect outweighs the shrinking effect caused by increased nuclear charge. So, atomic size increases on moving down the group. On seeing the table, there is a significant increase in atomic radius from carbon to silicon. This is due to the strong shielding effect of s and p electrons in silicon. The increase is relatively small from silicon to germanium. This is due to the poor shielding effect of d electrons in germanium. Similarly, the increase is not significant as in the case of tin and lead. This is due to the poor shielding effect of d electrons in tin. Also, poor shielding effect of d and f electrons in lead. As a result, the increased nuclear charge is more felt on the outer electrons of germanium, tin and lead, and therefore the increase in atomic size is less significant. The next general property is density. We know density is the ratio of atomic mass and atomic volume. As we move down the group, atomic mass and atomic volume increases. So, the effect of increase in atomic mass outweighs the effect of increasing atomic volume. So, density increases down the group. The next general property is ionization energy. Ionization energy is governed by three factors: the charge on the nucleus, the amount of screening by the inner electrons, and the distance between the outer electrons and the nucleus. As we move down the group, nuclear charge, atomic size and screening effect increases. The combined effect of increase in atomic size and screening effect outweighs the shrinking effect caused by increased nuclear charge. So, ionization energy decreases on moving down the group. The first ionization energy decreases down the group up to 10. Due to increase in atomic size, then there occurs a slight increase from tin to lead. The irregularity arises due to the shielding effect of inner electrons. For example, the shielding effect of S and P electrons in silicon is large, so there is a sharp decrease in ionization energy from carbon to silicon. The shielding effect of inner d electrons in germanium as well as tin is poor, so there is a decrease in ionization energy from silicon to tin is not much. But in the case of lead, the shielding effect of F and D electrons in lead is very poor, so there is an increase in ionization energy from tin to lead. The next general property is metallic character. As we move down the group, ionization energy decreases and metallic character increases. Here, carbon is a non-metal, silicon and germanium are metalloids, tin and lead are metals. The next general property is oxidation state. All the group 14 elements show an oxidation state of +4 and +2 in their compounds. The stability of the +2 oxidation state increases on moving down the group due to inert pair effect. Then what do you mean by inert pair effect? The reluctance of ns electrons to take part in bonding due to the poor shielding effect of intervening d and f orbitals on moving down the group is known as inert pair effect. The next general property is standard electrode potential. The standard electrode potential are defined by measuring the potential relative to a standard hydrogen electrode using 1 mole solution at 25 degrees Celsius at 1 atmosphere pressure. The larger the value of the standard reduction potential, the easier it is for the element to be reduced by gaining electrons. These are oxidizing agents. The smaller the value of the standard reduction potential, the easier it is for the element to be oxidized by donating electrons. These are reducing agents. As we move down the group, standard reduction potential increases. Here, there are two types of standard electrode potential values are marked in table. First one, metal in +4 oxidation state to +2 oxidation state. In the second one, metal in +2 oxidation state to metal. Here, high positive value of standard electrode potential in M4 plus to M2 plus of lead indicates that Pb4 plus to Pb2 plus reduction is easier than Sn4 plus to Sn2 plus reduction. The negative standard electrode potential for M2 plus to M values indicate that both metals must be capable of displacing hydrogen from dilute acids. The next general property is electronegativity. As we move down the group, electronegativity decreases from carbon to silicon due to significant increase in atomic size. The increase in atomic size from silicon to lead is not very significant, so there occurs no significant change in electronegativity. Due to smaller size and higher ionization energies, the elements of group 14 are slightly more electronegative than corresponding group 13 elements. The next general property is melting and boiling points. On seeing the table, it is clear that the variation of melting points is not regular. The melting point decreases from carbon to tin due to the gradual change from covalent bonding to metallic bonding on moving down the group and the weakening of the bonds between atoms with increase in atomic size. Melting point increases on moving down from tin to lead due to poor screening effect of lead. Lead has a cubic close packed structure which is more tightly packed structure than body centered cubic packing in tin. The next general characteristics is catenation. Catenation is the linkage of atoms of the same element into longer chains. Catenation occurs most readily in carbon, which forms covalent bonds with other carbon atoms to form longer chains and structures. Carbon has very great capability for catenation. That is why carbon is able to form an immense array of organic compounds. Silicon has much less capacity for catenation than that of carbon. The silicon linkage is up to 10 silicon atoms. Germanium has a little lower tendency to catenate, while tin and lead show virtually no tendency for such type of self-linkage. Catenation capability depends on electronegativity of the element, types and shape of orbitals involved in bonding, hybridization involved, and bond energies. The carbon-carbon bond energies are much higher compared with those of silicon-silicon, germanium-germanium, tin-tin, and lead-lead bonds. This is because on descending group 14, orbital overlap becomes less efficient as the valence orbitals becomes larger and more diffuse. So, the tendency for catenation of an element of the group would decrease with the decrease in bond energies, leading to the catenation capability order. Carbon is very greater than that of silicon, which in turn greater than that of germanium, which in turn greater than that of tin and lead. The next general characteristics of group 14 element is allotropy. Allotropy is the existence of two or more different physical forms of a chemical element. Carbon exists in different forms, crystalline and amorphous. The different crystalline forms are diamond, graphite, fullerene, CNT. The different amorphous forms are coke, carbon black, charcoal. Tin exists in two allotropic forms at room temperature and pressure, alpha tin or grey tin and beta tin or white tin. Alpha tin is the stable form below 13.2 degrees Celsius, while beta tin is the stable form at ordinary temperature. Under normal condition, germanium has only one crystalline form called alpha germanium. Alpha germanium, which has a metallic luster and a diamond cubic crystal structure, the same as diamond. At pressure above 120 kilobar, germanium becomes the allotrope beta germanium with the same structure as beta tin. Next, we can discuss about the chemical properties of carbon family. The group 14 elements have Ns2, Np2 outer electronic configuration. So, each element in the carbon family has atoms that gain, lose or share 4 electrons when reacting with other elements. In group 14, only carbon atom is a non-metal. Firstly, we can discuss about the reaction with water. Carbon, silicon and germanium are unaffected by water. Tin reacts with steam and to form stannic oxide. Lead is not affected by air-free water at ordinary temperature due to the formation of an unreactive layer of oxide on the metal surface. It slowly decomposes steam at a high temperature. Water containing dissolved oxygen corrodes lead slowly, forming lead hydroxide. Lead hydroxide is soluble in water to some extent. The ability of a solvent, for example water, to dissolve lead is called Plumbo solvency. It becomes a great health hazard when public water supply system uses lead pipes for water transportation because lead is a highly toxic metal. Plumbo solvency increases when water contains dissolved nitrates, ammonium salts and organic acids. Plumbo solvency decreases when water contains phosphates, carbonates and sulfates. The decrease is due to the formation of an protective coating of insoluble lead salts on the surface of the metal. The next one is the reaction with the hydrogen. There is no direct reaction at ordinary temperature with hydrogen. But carbon combines with hydrogen at the temperature of electric arc producing methane. Carbon forms a number of hydrates. All other elements form tetravalent hydrates. The stability of hydrates decreases and reactivity increases on moving down the group. The next is the reaction with the halogen and the formation of halides. All the group 14 elements form tetrahedral and covalent halides of the formula MX4. Here CCl4, carbon tetrachloride, does not undergo hydrolysis due to non-availability of d orbital. Silicon tetrachloride and the halides of heavier elements can undergo hydrolysis due to availability of vacant d orbital. Silicon tetrachloride on hydrolysis gives silicic acid. Lead tetrabromide and lead tetraiodide do not exist because lead 4 plus is a strong oxidant and Br minus and I minus are strong reductants. Apart from tetrahalides, germanium, tin and lead form dihalides MX2 type. The stability of the dihalide increases steadily on moving down the group. This is due to the inert pair effect. Due to inert pair effect, the plus 2 oxidation state is more stable than that of plus 4 oxidation state. Carbon tetrahalides are kinetically more resistant to hydrolysis because of the lack of access for water to the carbon atom to form an intermediate complex, because carbon has no d orbital in its valence shell. The other group 14 tetrahalides are easily hydrolyzed by water because the central atom has empty valence shell d orbital. So, they can accommodate the lone pair of electrons from the water molecule in a d orbital. For example, silicon tetrachloride undergo hydrolysis probably by initially accepting lone pair of electron from water molecule in a 3d orbital of silicon to form an intermediate, which gives off a molecule of HCl and to yield SaCl3OH. The process then continues in a similar manner, finally leading to the formation of silicic acid. Due to the absence of valence shell d orbital, carbon cannot expand its covalency beyond 4, but others can. For example, silicon can form hexafluorosilicate ion due to the presence of 3d orbitals. But hexachlorosilicate ion is not formed because 6 large Cl- ions cannot be accommodated around silicon 4 plus ion due to limitation of its size, and thereby the interaction between the lone pair of chlorine minus ion and silicon 4 plus ion is not very strong. Today we have discussed about general characteristics of group 14 elements. In the next part, we will discuss about different allotropes of carbon. Thank you.